So we are now going to talk about magnetic fields. We've been talking about electric fields and potential and circuits and all that stuff. We're now going to transition to magnetic fields. And the way our course is set up, we talk about electric fields, then we talk about magnetic fields, and towards the end of magnetic fields, we kind of see how those two kind of come together. That electric fields give you magnetic fields, and then magnetic fields can give you electric fields, and that is the beginning of understanding electromagnetic waves. Okay, so eventually we're gonna work to the electromagnetic waves. We're not talking about wave theory in detail in this class. We'll say that that's for physics 3C. But at least we're going to see how the electric field and magnetic field kind of marry and see how they affect each other. Okay, so now we're focusing on magnetic field today, and this first lecture is more of an introduction to magnetic fields, just getting us used to seeing it, seeing how magnetic fields work, where they come from. So we're not going to get too much into the meat of it. We'll save that for our next lecture. All right, so I think it'll be best to kind of start off with this PowerPoint that I have here. Oops. And again, this is more of an introduction to this topic. We're not going to dive in, but just a kind of soft intro into this. Okay, so this is chapter 20. Obviously, this is not for chapter 20. We're talking about what is this chapter? Chapter 29, I think, in the 4th edition there. Okay, so let's see. Okay. All right, so first I want to talk about where magnetism comes from. Now, really, in order to really understand where it comes from, we have to talk about electron spin, go down to the down to the electron level. So we're not going to go into that much detail, at least not now. We will a little bit at the end when I touch on ferromagnetism, diamagnetism, and paramagnetism. So we'll talk about that at the end of I think it's chapter 29. So for now, we're just going to kind of talk about generally where magnetic fields come from, and it's a magnet, right? So pretty simple there, not talking too, like I said, too much in detail. And of course, magnets, that it has a north pole and a south pole, and we know how they behave. So north poles, of course, repel. North and south poles, of course, attract. All right, so the whole point of showing you that is not to really teach you this, because I think most of you know from experience. I think my 5-year-old or 6-year-old son knows that from experience. So it's not to teach you that, but I hope you see kind of a similarity with what we've been talking about as far as electric fields go, right? Electric fields, you have two positive charges, two like charges, and they repel, and then you have two opposite charges and they attract. Okay, so something very, very similar, and extrapolate that a little bit, right? When we talk about charges, we said, well, they're interacting with each other's electric fields. Well, we can see here, kind of make the same jump. These magnets have magnetic fields, and they're going to affect the magnetic fields. Okay, so we're going to look at that as well. So that's kind of where we're headed. Okay, so like this is what I just said, right? Similar between charges. Okay, now one issue about magnets that we can't have, that we do have with charges, is you can't isolate a pole. You can't have a north pole by itself. You can't have a south pole by itself. Once you cut a magnet, and I think I have a picture of this here. Once you cut a magnet, let's say you see in my picture there, I'm cutting a magnet right down the middle, north pole on one side, south pole on the other. You cut that magnet, and what's left is another magnet with another north pole and another south pole. And you keep cutting these in halves and keep going down. You won't ever get a north pole by itself, and you don't ever get a south pole. Okay, so in terms of when we talk about magnets always exist in dipoles. They do not exist in monopoles. Okay, monopoles being a north pole or a south pole. Whereas positive charges and negative charges, you could have a positive charge and negative charge existing in space, and not necessarily having the negative charge, right there next to it. You can have a positive charge just hanging out in space by itself. Okay, so that positive charge is a monopole, right? Electric fields will be coming out of it. With magnets, you can't get that north pole or south pole by itself. So there is a difference between, electric fields and magnetic fields, and we see that in particular. I'm going to touch on this later with Gauss's law. Okay, there is a Gauss's law for magnetic fields, and for Gauss's law for magnetic fields, that the flux there always equals 0, because if you have a magnetic field, you always have magnetic fields going out, magnetic fields going in, because there's always a north and south pole in that magnet. Okay, so I know I kind of jumped ahead there, but what I want to say is that this little picture that I have here has really big implications about how we treat magnetic fields. All right, so let's keep going here. So how do we detect magnetism? Well, with another magnet. Okay, so magnets interact with what we call magnetic fields, and I think I have a picture. Oh, well, this is pretty much what a compass is. You have a magnet here. That magnet is going to align itself with a magnetic field. Okay, I know I have a picture coming up. That was in this slide, but not yet. Okay, so I have the North Pole points towards the north, right? South Pole points towards the south. And it's essentially what a compass is, right? When we look at a compass, we're just seeing we're just having a magnet, a magnetized, metal that's able to move around, to, I guess, swivel would be the right word, right, to rotate there, and it's going to always align itself with a magnetic field. Okay, so I know I have a picture. Here we go. Okay, this is the picture I was looking for. So when you're talking about magnetic fields, there is, even though you can't have a north pole and a south pole, there is a similarity in that there is a similarity with electric fields in that magnetic fields always originate from the north. So we're going to say magnetic fields come out the north here. You can kind of see that there, and go towards the south. Okay, so very similar to electric fields, right? For electric fields, we say electric fields exits the north, or it comes out the, when I'm talking about electric fields exit the positive, goes towards the negative, right? And that would be like in a dipole situation. Well, kind of the same thing here. Magnetic fields comes out the north, goes towards the south. And as you see these lines, the more spaced out these lines become, the weaker the magnetic field, right? Very similar to what we talked about with electric fields. So you have weaker magnetic fields here, very strong magnetic fields as you get closer to the magnet, right? And that should make sense. That should be intuitive. It lines up with your experience that as you get closer to a magnet, right, magnetic field increases there. Okay. Okay, so this is how we would draw the magnetic fields. Right, we have a magnetic field going from the north to south, and here is very similar to a dipole. In fact, you saw this in one of your labs when you had to do the equal potentials, right? You had to plot the voltages, and then from the voltages, you draw the electric fields. Well, you should have seen an electric field very similar to this when you had a positive charge here and a negative charge here. Right, so here is very similar. You have magnetic fields coming out the north, magnetic fields going towards the south. Okay. And so here's kind of the opposite picture. You have two norths. Magnetic fields just are repelled, right, from that other north. Right, they do not want to go towards the north. They want to go towards the south. Okay, so that's why the magnetic fields kind of repel there. And there you go. All right. So let me see here. I'm going to jump ahead and talk about another source. So one source of magnetism is the, oh, you know what? I do want to show one picture before I leave that. And that's a picture of the Earth, because I think it's interesting. All right, so here's the Earth. And of course, you know that Earth, maybe, I'm sure you know, Earth has a magnetic field. And that magnetic field goes around it. What maybe you didn't know is that when we talk about the North Pole, the geographic North Pole, right, going north, this North Pole right here, that is not the same idea or same meaning as the magnetic North Pole. So if you look at, here's the magnetic field of the Earth right here. If you had a compass, right, that compass aligns itself to this magnetic field. All right, so I'm going to draw how a compass would align itself to this magnetic field. Remember, north always points in the direction of magnetic field, so I'm going to have my north going like this. Let's see. There you go. So your compass will tell you to move up north. Now, like I said, that's not the same thing as magnetic north. If you look at these magnetic field lines, the magnetic field on Earth comes out here at the geographic South Pole, goes up, and then goes near. It's not quite at the North Pole. It's a little bit off, but it goes towards the geographic North Pole. Okay, so if you imagine a magnet in the Earth, where we have the North Pole is actually where the south side of the magnet is, and where we have the South Pole is actually where we have the north side of the magnet. Okay, so when people talk about North Pole, they're talking about the geographic North Pole. That's different than we talk about the magnetic North Pole or the magnetic South Pole. Okay, so I thought that was kind of interesting to, we're talking about magnetic fields, and when we apply it to the Earth, it's a little different there. There is some talk, which is always, I find it interesting, about that magnetic field changing, or the South Pole here changing. It has changed quite a bit, especially in recent years, and maybe I'll find that there's a really cool map that shows you how that South Pole has changed geographically. And then you do a little bit of digging, you'll come up across this idea that this magnetic field, this magnet in the Earth, can flip, and it has flipped in the past, and we can see that from geology. There is evidence of this magnet flipping directions and flipping kind of rapidly. So there is some talk about this magnetic field changing and what that would mean for our devices, for things like GPS and all that. Some people think it's going to be a disaster. Some people think it's not going to be that bad. So anyway, if you want to do a little Google search on the magnetic field of Earth flipping, the flipping polarity of Earth's magnetic field, you get some interesting talks. I would avoid Reddit though. Probably not the best source there. Okay, so anyway, well, let's move on. Okay, so another source of magnetic field. So one of the sources I said was a magnet, right? And of course, we could talk more in detail about that, looking at the electron spin and how that creates a magnetic field as well. Okay, but moving on from magnets, another source is charges. So charges can create magnetic fields, but there's certain conditions that must apply. The charge has to be moving. Okay, so here's kind of the discovery of this. This guy, I think in the 1800s, named Ørsted. Ørsted was going to give a demonstration to his class, and I have to go back and look at the history of this. Some people say that it was while he was giving a demonstration. I think I read that he was preparing to give a demonstration to his class. Anyway, he was going to give a demonstration to his class about that magnetic fields and electric fields are independent from each other, which is not true. So he was going to do this demonstration, and he starts off here with this picture, and you have current flowing through it, and he put compasses around it and says, okay, there's no current. Sorry, there's no current right now, and then you have this compass. So these compasses, of course, line up to magnetic north, or they line up to the magnetic field, pointing you to the magnetic South Pole. And so that's not surprising. So right now, do I have charges in this wire? And the answer is yes, there are charges in the wire. They're not moving as far as they're not moving in a uniform way, right? There's no current there. So we don't see any magnetic field. Now, Orsted turns on this wire, right? Connects it to a power supply, turns it on, and all of a sudden, those magnets start to change direction. You start to have these magnets kind of point in a circle around this wire. So the takeaway here is that charge has this strong connection with magnetic field, and that connection to magnetic field is what we're going to be talking about in our class here. So moving charges in particular create a magnetic field around it. I think I have that here. Okay, so only when there's moving charges. If the charge is stationary, it does not create a magnetic field, but if the charge is moving, right, has a certain speed, then that charge creates a magnetic field. That's why we didn't see a magnetic field here. This is just a magnetic field of the Earth. And then now, when I turn on this wire, then I see a magnetic field. Okay, so Orsted made that discovery. And then I think it was not that much longer later, we have these two people, and this is, I'm gonna have to go off my slides for this one. Two people kind of analyze that and give a mathematical formulation for this. So this is, maybe, I always mess up their names because I'm terrible with pronunciations. I'm pretty sure it's French though. Biot, I don't know, Savard? I can't remember in French, you don't pronounce the last thing, but okay, Biot Savard, they look at a wire. So let me draw a little axis here. Okay, so they look at a wire. Let's say this wire is kind of going along the z-axis. Okay, and then look at this little segment of wire here. Yeah, you don't need my face up here for this. Okay, so they look at this wire, and then they notice that a magnetic field is created. Let's say the current is going this way here. Okay, save my direction, my current. Okay, so the current is going, and I hope I draw this correctly. The current is going in the negative z direction. This will be my positive x here. This will be my positive y. So that current is going in the negative z direction. And what they note is at a distance r away from the wire, let me do a different color. Distance r away from this wire, you have a magnetic field going, it creates a magnetic field going down. Now, for magnetic field, we're going to use the symbol B. Now, let me do that in red here. Okay, so B is going to be our symbol for magnetic field. Okay, and the units for magnetic field. Put that here. Is a Tesla. Okay, so they do different currents, do different distances, and this is what they notice, that the magnetic field from this wire. I'm going to give it to you guys in terms of the moving charge first, and then we'll look at specifically a wire. They're really similar. That's supposed to be a B. So magnetic field from this wire equals this new constant that we're going to be running into a lot, mu0 over 4 pi times the charge times the charge of velocity, cross product r hat over r squared. Okay, so we're gonna have to explain this a little bit. So this mu0 here, our new constant, is called the permeability of free space, permeability, and it is the value for mu0 is 4 pi times 10 to the negative 7. Okay, I know you're asking, just from my experience in teaching, why do we have a 4 pi there and then divide by 4 pi? Well, that 4 pi in the denominator is not always going to be there. Okay, so this is our value for our constant. Mu0 is equal to 4 pi times 10 to the negative 7, and the units for this mu0 is Tesla meters over amps. Okay. All right. So so let me explain a couple of things here. So that's mu0. Then we have Q, which of course is a charge, right? This is a charge moving through this wire. So it's a charge. V is the speed, and notice it's a direction here. In this case, if the current is going this way, then we know you can either see this as positive charges moving this way, or more realistically, electrons moving in the opposite direction. Okay, whatever the case, we're looking at the speed of that charge. Okay, and then we have, okay, r squared is of course the distance that we talked about here, distance from your wire to your point of interest. That's what the r is. And then we have r hat. Okay, r hat. Well, remember how we define unit vectors? R hat equals the direction and magnitude of the vector r divided by the magnitude of r. All right, so that's my unit vector. And it really just gives you, a unit vector means the magnitude is going to be 1 of that unit vector. And it just really gives you direction. So this is just going to be the direction of r. Right, that's what that unit vector is. Direction of r. Okay, so which points from the charge, or the wire in this case, but from the charge to the point of interest. Okay, so that is a direction. So it is primarily direction. I mean, there is a magnitude of 1 there. Okay, but there's a direction associated with it. So what this means is that we're looking at the cross product. Looking at the cross product of V, right, the speed of the charge, and R. Okay, so we're going to talk about cross products here, talk about things like the right-hand rule. Maybe you remember that from your previous physics class, but we are going to use a right-hand rule there. Okay, so this is more of the formulation. So Biot of R, they give a mathematical formulation of what Ørsted observed, and it does confirm what he said. So let me put, before I actually do the right-hand rule, let's apply to wires. Okay, we could easily apply this equation to wires. So let's do that. Namely, what I want to do is put this in terms of currents. So this is great when the equation up here is great when you have a charge moving through space, right? And you have the velocity. But what happens when you have a current? Well, when you have a current, it's not too hard to see the connection. Remember what current is. Current is just the flow of charge per time, right? So Q over T. And let me see here. And V is just length over time here. Distance over time. Okay, so if I invert this, this becomes Q equals I times T. This becomes V. Well, I don't need to invert that. So this is I. So if I take this Q, plug it in here, take this V, plug it in for V, I get a different equation for B, but more applicable when it comes to charges. So, sorry, not charges, but to currents. B equals mu 0 over 4 pi. We still have that 4 pi there. I L cross product R hats over R squared. Okay. So that equation in the blue here tells us a magnetic field for a wire. And I think I only need to explain one thing here that I didn't explain earlier is this L. So what is this L? Well, this L is just the length of the wire. And you notice it has a vector there. So that vector is just telling us that's going in the direction of the current. So L is the length of the wire, and it goes in the same direction as the current. Okay, so let's try this out and see if we are able to notice what Ørsted observed. I'm going to draw a current coming out of the screen. So that's how I draw a current coming out of the screen. How do I draw a current going into the screen? Well, here's my wire. Let me do that a different color, actually. No, you know what? Blue's fine. Draw an X. Okay. So if you draw a dot means that the vector, in this case current, is coming out of the screen. If I draw an X, that means the current is going into the screen. All right. So we're going to use that notation quite a bit. And I want to do. Let me put a point here. Point P. Okay, all I want to do here is get us used to using that right-hand rule. Right? How do we use the right-hand rule to find out the direction of magnetic field? Okay, and of course, when I say right-hand rule, we're essentially doing the cross product here. Okay, so I'll try my best to show you guys how to do this with the right-hand rule. Let's see. Bring it. Okay, so the first thing we're going to do, there's actually a couple of ways you could do the right-hand rule here. So notice we have two vectors, right? We have L and we have R. These two vectors, which right now we just care about the directions. We'll talk about how to actually get a number for B later on. But right now I just care about the directions. L, remember, it's the direction of current. And if we're talking about this example down here, current is coming out of the screen. So I'm going to show you two ways to do it. So first way is called the chicken claw method. Okay, so for the chicken claw method, you have your fingers like this. Your thumb and your pointer represent those two vectors. Your thumb is the direction of your current, and your pointer finger represents the direction of the of R. Okay, which in this case R hat, points to you. Remember what I said there? It points from the charge or from the wire to the point of interest. So my R hat is going this way. Let me put that different color here. Okay, so that's my R. Okay, so your thumb represents your current, which is coming out of the page. So from your perspective, right, you should have your thumb pointing towards you, and your pointer represents R. Okay, so okay, good. Oh, okay. All right, so if I want to align this up, my thumb's going to be pointing towards you guys. It's going to be tricky. My thumb's pointing towards you guys here, so my thumb's pointing out of the screen, and my pointer, right, is pointing in the direction of R. Now, my middle finger here, which should be kind of coming out of your palm, right? So it's perpendicular to my palm, pointing straight out. This will always be perpendicular to these two fingers. Okay, so my middle finger coming out towards you guys will always be perpendicular to your thumb and should always be perpendicular to your pointer. And that is pretty much what the cross product does, right? The cross product gives you a vector that is perpendicular to the two vectors you're multiplying together. So in our case, we're multiplying L and R. And so our resulting vector, B, should be perpendicular to both L and R. Okay, so as far as the right-hand rule goes, what I'm saying is your middle finger should be perpendicular to your thumb and your pointer. Okay, so if that's the case, this thumb is representing your magnetic field. Okay, so your middle finger represents your magnetic field. So your thumb represents your current, your direction of current. Your pointer represents R, or R hat, and your middle finger perpendicularly outward should represent magnetic field. So if you have all that lined up, I'm going to line it up to the picture as you guys see it. So my thumb's coming out of the screen. Pointer is going to the left, and I have my middle finger pointing down. Right now, are you guys able to do that? Are you guys tracking there? All right. So what that tells us is that I have my magnetic field is pointing downward. So I would draw that here up on the screen. From the right-hand rule, we see a magnetic field is going down. Okay. That's what that tells me there, if I use the right-hand rule. Okay, well, I'm gonna do it one more time. Let's try it up here. So let's say here's my point P. Let me call it a different point, a different letter. Let's call it point R. Okay, point R. Of course, we have our lowercase r, right? Our radius pointing upwards now. Okay, so try the right-hand rule. Remember, and then I'll do it with you guys, but I'll give you guys a minute to try it yourselves. Thumb represents your current, pointer represents the R vector, and middle finger, this middle finger right here, represents your magnetic field. Okay, and remember, it's called the right-hand rule. Make sure you're using the right hand. I know it might look weird on the screen. Use your right hand. Sure. Okay. Thumb represents R. Let me start all over. Your thumb represents current, the direction of current. Pointer represents R, and your middle finger represents magnetic field, B. Let's try this out. So my thumb is my current, right? So again, my current is going out. Oh, I have to realize something. It's gonna look, oh no. Okay, current is coming out towards you. My R, right? My pointer is my R, which is pointing up. And as you guys could see on the video here, thumb's pointing out towards you, right? That's my current. My pointer is pointing up, that's my R. And look at my middle finger. My middle finger is pointing to the left here, right? So that's telling me that my magnetic field is going to the left. All right, if anybody wants me to repeat that, put it, tell me in the chat there to repeat, and I'll gladly do it. Okay, but using the right-hand rule, we get magnetic field going this way. Okay, so I'll do that one more time. So your thumb represents current coming out towards you guys, right, out of the screen here. R represents your R vector, which is, as you can see in the video on the whiteboard here, R is pointing up. So I have my thumb going out towards you guys, R is pointing up, and my middle, and make sure your middle finger is perpendicular, right? That's really important. If your middle finger is not perpendicular, this is not going to work. But the middle finger is pointing, as you can see, to the left there. Okay, so that is how I know that magnetic field is pointing to the left. Okay, it's a little kind of straining on the wrist sometimes. But okay, so there is another way of doing it. I'm kind of hesitant to teach you guys, but if that kind of messes up with your wrist, actually I think even on the video that I sent you guys, there's even another way of doing that right-hand rule. But let me okay, if you didn't like that, what I call the chicken claw method, which is not my preferred method, Let me show you another way. It totally doesn't matter which way you do it because you get the same answer at the end. But here is the way I would do it. Okay, so instead of twisting my wrist, this is a little bit easier. So I have my hand kind of like this. My thumb is perpendicular to my I don't know, my fingers here, right, making a 90-degree angle. And so keeping my hand like this, I put my whole hand in the direction of I. So current's coming out towards you guys, so put my whole hand there. Then I'm going to curl my fingers towards R. Now R is pointing upwards, right? So if I do this, I'm curling downwards. So that's not the direction. So I have to flip my hand upside down and curl towards R. Okay, so move my fingers upwards towards R. And you can see my thumb is pointing to the left, which is the direction of magnetic field. Okay, so that's an alternate way of doing the right hand rule. I'll do it one more time. Your hand goes towards the direction of I. You curl your fingers towards R, which is upward, right? Curl upward, and then your thumb points in the direction of magnetic field. Okay, so you could really do either way. I prefer the way I just did it, just because it's less straining on the wrist. You could do it pretty quickly. You don't have to figure out which vector is what. But either way should give you the right answer. Okay, so let me go back to this picture here. So if you do it everywhere, at different points around this, let's see. You do it different points around this wire in this circle here. Right, that pretend that makes a circle. And the magnetic field will always go in that kind of same direction here, or same rotational direction. Okay, so for a current coming out of the screen, it creates a magnetic field going, as you can see there, clockwise. Or sorry, that would be counterclockwise, wouldn't it? That'll be counterclockwise. And let's talk about this wire I have up on top of the screen, where you have the current now going in. I'm talking about this part right here. In this picture, current is going into the screen, and if we do the right-hand roll over again for different direction, okay, looking at different points around this. If we do the right-hand roll, now this time current is going into the screen. We just get the opposite direction here, where magnetic field will now be going clockwise. I don't know why I put so many dots. Okay. All right, so this is what Ørsted observed, going back to what I showed you in the PowerPoint, where he turned on current through a wire, and that current suddenly made the compasses go in a circle. It's because of this, because of that right-hand rule that we see here. Okay, now there are, I think, 3, maybe even 4 different right-hand rules in this chapter and in chapter 30. Okay, so that right-hand rule gets applied a lot of different ways, but I think it's important to remember that all we're doing here is the cross product. Okay, we're just looking at the cross product. So you could do the chicken claw for every single cross product you do, or your thumb is a first vector in that cross product, your pointer is a second vector in that cross product, and then your middle finger is the actual is a resulting vector, right, that you get from the cross product. Okay, so you keep doing that. Okay, so what does the circle with the X mean again? The circle with the X is telling us that the current is going into the screen. Yeah, going into the paper, that's right. All right, so, and that's kind of the typical notation we're gonna use, not just for currents, but also for magnetic fields. If there's an X, it means that vector, whatever vector we're talking about, in this case currents, it means that vector is going into the screen. If you see a dot, that means that that vector is coming out of the screen. Yeah, you're welcome. So I know that could get a little, I know when I took this class as a student, I had a hard time for some reason remembering that. And I don't know, this might not work for you, but what I thought of was a kind of like a dart. If I'm looking at the dart coming towards me, what I see is something like this, right? That little dot here is a point, is a middle of the dart, right, coming out towards my eyes. So that helps me remember. If I see an X, that's where I want to throw the dart, right? So it'll go into the screen as I threw it towards the X. So that's what I used to help me remember when I was a student, and it worked. But you know, do whatever whatever helps you remember. Okay, so X means going into the screen. A dot means coming out of the screen. All right, let's see. Let me wrap this up by showing you one more right-hand rule, which kind of summarizes this. So we figured out, this is kind of what we did here was I would say the long way of figuring out the direction of magnetic field. There is a shortcut we could take, but now that you know where the details, let me show you one other thing here. Go back to my PowerPoint. Okay, so quick way of using the right-hand rule without using the cross product. It's pretty much this. If you put your thumb in the direction of current, right, almost like you're grabbing that wire, the way you grab that wire and the way your fingers curl will tell you what direction the magnetic field is going. So in this case, you can see in this picture, current is going up. So you grab that wire, and as you grab that wire, your fingers are going to be going in that, I don't know, that would be almost like a counterclockwise motion there. Okay. So you can figure out pretty easily that the magnetic field created around it is going to be clockwise or counterclockwise or whatever. Okay, so let's apply it here. I think I have a. So this is what, okay. So this is a picture we had earlier, right? In the PowerPoint, or not the PowerPoint, in the, what was it called? The whiteboard. We had a current going into the page, right? That's what the X means. And current going into a page created a clockwise magnetic field. That shaded region of that needle, this is kind of like a compass, is a north direction. So that's telling me my magnetic field is going in that clockwise direction there. So how would I know that using that right-hand rule I just showed you? Well, if current's going in, going into, so from your perspective, coming this way, current is going into the page, right? So I have my thumb pointing into the screen here. The way I curl my fingers, right, will tell me whether that's clockwise or counterclockwise. So as you can see, my fingers kind of are curling in that clockwise direction, right? At least from hopefully from your perspective it is. Okay, so I'll put my thumb direction of current going into the screen here. That's what the X means. And then you can see my fingers curling in that clockwise direction. Okay, so like I said, this is kind of that shortcut where you don't have to do the cross product for every single point around it. You could just do this, and you see that you get a clockwise rotation. Okay, you can even work backwards here. Let's do this one. Okay, so you can see a magnetic field, right, is going, in this case, what would that be, counterclockwise. So if you're going to use your right-hand rule and go counterclockwise, like this, all right, with your right hand, curl your fingers counterclockwise. In order to do that, your thumb has to be pointing out of the screen, right? If you want to go counterclockwise with your fingers, like what I'm doing with my hand here, notice my thumb. My thumb's pointing out towards you guys, right? So you guys are going to be getting sick and tired of looking at my hands. Okay, so counterclockwise, thumb pointing out towards you guys. That gives me my answer. Right? Your thumb represents current. So if my thumb is pointing out of the screen, then I get my answer. All right, it's going out of the screen here. Okay, so that is the right-hand rule. I think we're let's take a break. We're going to take a break. When we come back, I have a couple examples that I want to work through, and then we'll stop there and end our lecture for the day.